So this is how to deal with energy. Now there exists perfectly good equations that I think the IB should give you for solving energy problems, right? I mean, quite simply, what's really going on is that the total energy of the oscillator at any given point, right, is its kinetic energy plus its potential energy, right? Now, IB chose not to put that formula in the data packet, which makes all of the other formulas very obtuse. Imagine teaching about simple harmonic motion when you don't have the formula for the potential energy, right? Now, the way this works is, let's suppose that at any given instant, right, it's got some total energy. Let's suppose that that energy adds up to 10 joules, right? Somehow we add it up, right? If we've got 2 joules of kinetic, point your eyes up here, don't write those things down yet. We'll write them down as we go. Okay, if you've got 2 joules of kinetic, how much potential do you have?
8.
8. What if you've got 4 joules of kinetic? How much potential do you have? 6. What if you've got 9 joules of kinetic? How much of this do you have? 1 of those, right? It always adds up to the same number. It always adds up to the same number. This is the key concept. Now, if you look at the data packet, one of the things they give us is that the total energy is, the kinetic energy, the E total, right, is 1/2 m omega squared x naught squared, right? Now, if you think about this, this is the amplitude, right? Somehow, doesn't this formula have to be 1/2 kx squared in some weird, twisted way? Right? Isn't your total energy, the maximum energy is going to be 1/2 k amplitude squared? Why is that true? Why, when it's at amplitude, is it all potential energy, and why is that the total energy? Because what's the kinetic energy when you're at the very edge? There's no kinetic energy at the edge. Why is that? Why is that? It's not moving at the edge, because if it was moving, it'd not be at the edge. It'd be on its way there or on its way back from the edge, correct? So at the edge, when it's at amplitude, it's not moving, it has no kinetic energy, all the energy is potential energy, correct? And so this is the total energy, right? So how, in the name of heaven, do they get this big complicated formula? And what, and omega, and holy cow, right? Okay, well, here's the thing that you don't know, okay? And that is that omega is equal to the square root of k over m. Everybody else in the world gives you that formula, there it is, right? Okay, and you can derive it from these things, but it's pretty roundabout. This makes everything work, doesn't it? Okay, 1/2 mass times the square root of k over m squared times x naught squared. I'm pretty sure that boils down to this, doesn't it? Sweet mother of the Savior, right? Okay, this is very, very deadly simple. They couldn't have made it more confusing, okay? But there it is. That's the formula. There it is, right? Okay, so that's where this comes from. And then there's another formula that says the kinetic energy max is 1/2 m omega squared x naught squared. Like, is that the same formula? Yeah, the total energy is going to be the maximum kinetic energy, isn't it? Isn't that right? If it's got 10 joules of total energy, what's the maximum kinetic energy that it will have? 10 joules, because it's going to have that when the potential energy is 0. And where is that? Where is the, if it's oscillating back and forth, okay, where is it that it has maximum kinetic energy? Right in the middle. That's maximum kinetic energy, right? In fact, it's got all kinetic energy, it has no potential, right? Where does it have the most potential? At the edges, right? Here it is. Here it's got potential energy, the maximum, right? Right? As it oscillates back and forth. Okay? So another way to look at this thing is, isn't the maximum kinetic energy is just 1/2 mv naught squared, isn't that right? Isn't the maximum kinetic energy 1/2 mass times the maximum velocity squared? Yeah, this is pretty basic, yeah? Isn't that right? Okay, and isn't V naught omega x naught? Isn't that right? Plug that in there, do you get this? Do you? Yes, you do. That's crazy. You're going to get this formula, right? So now the question is, how do you find, there's another formula there, and it's EK at any given position. That's the top one there. That's the $1 million formula, right? And IB is just so clever. So the kinetic energy, when it's not the maximum, right, is 1/2 m omega squared x naught squared minus x squared. Well, gee, where do they get that formula? Couldn't you just say 1/2 mv squared and plug this formula in for v and you'd get that formula, wouldn't you? Does that make sense? Right? You could plug that formula in there and get that, but then it's like, well, where did this formula come from? Well, it came from God. No. Let me show you where this formula comes from, okay? This is just the simplest idea. They have twisted this and made it just very, very hard to understand, right? Our total energy is going to be 1/2 k x naught squared, right? That's the maximum potential energy, correct? Yeah? That equals the kinetic energy at that point plus 1/2 k x squared, wherever it is now, right? Isn't this the total energy? The maximum potential energy is the total energy, correct? Yeah? Because when it has maximum potential energy, it has no kinetic energy, correct? It's at the edges, so that's that, right? Solve for this. Well, gee, it's 1/2 k x naught squared minus 1/2 k x squared. In other words, it's the maximum potential energy it's got minus the potential energy it now has. And you've already done this, right? If it's got 10 joules of total energy, and 2 of that is potential, how much kinetic does it have? 8. There we have it, right? Okay, so this equals our kinetic energy. Doesn't this turn into this? We got to do a little wangling, but doesn't it? Yeah? Can I factor this out? I've got 1/2 k, and then I've got x naught squared minus x squared, right? And then we've got to somehow get omega. Well, it's omega times the square root of k over m squared. Is that the same as k? Yeah, isn't that a lot simpler than this thing? Yeah, it's a lot simpler, isn't it? Okay. So I don't know why they teach it this way or do it this way, right? I think that Wales is a very desolate place, right? And so, I don't know. I really don't know. I think it is an act of desperation. Maybe it's a cry for help. I don't know. Okay, hopefully they're not watching these videos. Okay, but there we have it, right? So things that you should have. I think you should know that the energy is 1/2 mv squared plus 1/2 kx squared. I think you should know that the potential energy is 1/2 squared, right? Stuff like that, right? Anyway. I mean, it's just such a simple thing. The hardest thing is actually explaining, right? So let's do our, I think you have this example. So if you look on your sheet, you've got an example problem. Let's solve this example. It's on the back of the example problem you did last time. I've got extra copies if you need one, right here. Okay. No, you're not going to turn them in. They're just for your reference. Okay, a simple show. Okay, don't be calling somebody a non-simple harmonic oscillator. That's a hoe, right? Okay, has an amplitude of 0.48, so that's x naught is 0.48. And a mass of 1.12, so mass is 1.12. Everything's 1.12 because that's just, periods, masses, everything, okay? Okay, and then our period is 0.86 seconds, right? So that means our omega is 2 pi over 0.86, and we're ready to go, yeah? Okay. So the first thing says, what is its angular velocity? Well, for A, its angular velocity is going to be omega is 2 pi over 0.86. And we could store this in our calculator. So 2 times pi divided by 0.86. And that's 7.306. How many sig figs do we have? We have 2. So 7.306 should be an adequate number of sig figs. That's radians per second, right? I'm going to store that in A, but I'm so OCD that I'll never use an exact value, right? You guys on your tests, so have no problem rounding a value and then using it over and over again, okay? What is its maximum kinetic energy? Well, that's this guy here, isn't it? Yeah? Okay, EK max. So I'm going to go ahead and use a formula from the data packet, even though I just ragged on it. Okay, x naught squared.